Hello again, my name is Rick Gary. I'm with 4DSP. 4DSP is a company dedicated to providing FPGA-based technologies, both hardware and software, subscribing to VITA standards, as well as systems integration and design engineering services. Looking forward to meeting everybody today, so I'm going to kick it off and talk about how to go from a lab bench to an aircraft pod using VITA technologies. I really don't envy system developers because they really have a tough task. They need to be aware of so many different technologies, not only from the past, but where they're headed towards the future. They need to understand what are the various elements that need to be put together in order to deliver a system on time, on budget, with the reliability that's expected. And in our case, 80% of our business is in military, so as you can imagine what those requirements could be. So I wish it were as easy. I have a 10-month-old to just take the two pieces and put them together, but it's just much more complicated than that. Different technologies and constraints that need to be made aware of is, we're going to hear a lot about swap. We see it all the time. So an understanding of the actual environmental constraints where every inch, every ounce, every watt needs to be preserved to ensure that a mission can work in the time allotted, to how to figure out how to get the data into the system. RF technology continues to advance. Once you get it into the system, how do you digitize it? How do you communicate between all the different elements of the system? How to take advantage of the latest and greatest technologies for digital signal processing, doing it deterministically, in an environment where bandwidths continue to increase and frequencies continues to also increase, and having to do it faster and faster, especially with changes as we see today from LVDS to JESD. Latency could become a challenge as well. Deciding what to keep, doing it in a secure manner, all in all, designing a system that's going to be maintainable for the future. So definitely tough, but the good news is that through standards and subscribing to standards, the job is made much more efficient, much more effective. Systems can be developed and deployed much more quickly for all of the most demanding applications. So as part of this development process, subscribing to a standards-based company definitely has its advantages, especially since system developers are going to face a lot of challenges. So starting to see a lot of movement towards, especially in the military, going towards COTS and standard-based suppliers. And one of the main reasons is that it helps mitigate risk throughout the entire process. So an example, I'll go through some examples to start. There are many suppliers typically that work under standards, so the fact that developers have a choice of many vendors is a big benefit to them, obviously mitigating the risk of issues with one of the particular vendors, but at the same time, it reduces costs, as obviously there are going to be options, and this is now extended both to both hardware and software with innovations such as AXI, which allows for interchangeability of IP cores, for example. Working with vendors that have a broad customer base is also important because companies that have many customers obviously are going to learn from these different customers, take in those recommendations, package them up, be able to sell a new product out to their existing customer base. So many companies can benefit, and then upgrades and improvements become much more simple. Companies that subscribe to standards obviously hopefully provide a path to ruggedization and reliability, especially in this case, it simplifies the development process such that products can be reused both in the lab and in deployment. We'll talk a little bit more in the case study that we're presenting. Future-proofing is a key point, obviously, at least in the military, of course, to be able to leverage commercial technology as quickly as possible. So systems need to be designed in order to do that. Again, to be able to take advantage of state-of-the-art technology and minimize upgrade costs. Life cycle support is also important. By working with standards-based companies, typically there's backward compatibility that simplify the process and minimize the impact of obsolescence and how to dispose of systems. And finally, companies that subscribe to standards can offer shorter lead times. So the time required to put projects together continues to condense. So companies that subscribe to standards hopefully we'll have products in inventory and enable systems developers to make sure that they can get product on time and be ready for their missions. So I took the Houston We Have a Problem theme to heart and wanted to highlight a case study of a customer that had a particularly challenging problem to solve and how VITA technologies were used in order to solve that problem. So the challenge was to design a powerful electronic warfare platform to fit in an airborne pod. So electronic warfare is one of the main weapons in the military arsenal. It's an area that has a lot of research and also a lot of benefit in areas such as attack, protection, and support, and a wide variety of applications. And I could probably throw all the acronyms at you, but you already know them. But one of the biggest challenges is that as the trend towards wider bandwidths and higher frequencies require a lot more computing power to fit on the transport vehicles where they typically reside. So if we were to look at a real basic EW system, typical elements will include some kind of RF front end that then gets down converted. The data gets converted to some digital mechanism. It gets transported to the FPGA. That gets converted back out, and then in some kind of technique or some kind of advanced algorithm is applied. So once the block diagram is developed, the algorithm's developed, the next step is to go in the lab and prove it out. So in the lab, obviously, it's a great place. You have access to all the technology. You're sitting in air conditioning. So it's very simple, not simple, it's very relatively straightforward to take that algorithm and translate it to a lab system. However, the challenge is, how do we then take that lab system, shrink it, and then place it on a pod? So the traditional path has been, we take the prototype system, but then now a custom board has to be developed. Well, why not take advantage of the modularity of the various VITA standards in order to take the same fundamental components, you minimize the overall development time, and you get the same level of performance on the pod? And that was the task. So first thing was to determine what the requirements were. So in this particular application, it was a high-end application. So it was necessary to build a multi-gigahertz wideband transceiver. So in this scenario, the range was 100 megasamples per second to 18 gigs. So it was a very broad range of spectrum. At the same time, it was a lot of data that needed to be acquired. 2.5 gigahertz of analog bandwidth was necessary to do this. Since this was a high-end application, all the necessary horsepower for doing the collection, for doing the analysis was required. So at the time, it was the latest and greatest processor technology, GPU, Vertex 7 for the FPGA. And again, it had to fit on a 9-inch diameter pod, the 167 being one of the most common in the armed forces. So by having this platform, it could be reused in a wide variety of applications. Obviously, the environmental constraints, it had to meet all the MIL standards required for this environment. And again, the importance of being able to handle the computational complexity required for the various techniques that were going to be deployed, and having a future path to all the latest and greatest technologies. So what was the solution? Well, using VITA standards. So the VITA standards provide modularity roadmaps for the future. The technologies used included FMC, 3U VPX, modular backplanes, and the other key point was the way the system was developed. So it was a phased approach, and we'll go into more details of how this helped this particular customer solve their problem. And another key point was working with collaborative vendors. Again, standards enable that process. There was a lot of innovation required in this project. Products were needed to be designed to meet some of these stringent technical expectations, specifications. So the FMC technology was a very core element. By nature, it has obviously the small form factor that would make it easy to go from the lab environment out to the deployable system. It also, as per the standard, it's defined to be easily multiple type of environmental cooling, in this case conduction cooled, because again we're limited to the amount of environmental cleanliness in the pod. The other key points is it was open for multiple FPGA intercapability. So while this system was designed for one FPGA manufacturer, it enabled the possibility of using other in the future and being able to use new developments in FPGA like we're seeing with UltraScale and Altera's technology as well. FMC can adapt to a wide variety of functionality. In this case, it was only used for I/O, but it could you could easily use FMC to do synchronization between the various channels that were being acquired. You could also use it for communication, whether it's optical transceivers or Ethernet. And then the fact that it is a standard, there are many companies that have FMC modules out there providing lots of options to the customer, and it's a standard that continues to be evolved with 57.2 enabling further interoperability and a 57.4 FMC Plus, which enhances the functionality. So the FMC was mated with the VPX, in this case 3U VPX, again, due to the size constraints, but still with a very large amount of power, not only for transferring data, but also doing the analysis. Through OpenVPX, there is a pathway to ruggedization, again, simplifying the migration from the lab to the field with standards, bandwidth, connectivity, and interoperability that not only would enable this specific engineer to do his job, but also create a platform that others within the armed forces could use. So definitely through the combination of VPX and FMC, it's very powerful in the sense that you can have the same core plug-in board. By simply replacing the FMC, you essentially amplify the functionality of these two essential components. So in terms of the actual phases of the approach, as I mentioned, the first step was to create the lab system where the functional verification was done, algorithms were proved out. The core elements of the system included a 6-slot 3U VPX system off the shelf, again interchangeable, multiple vendors available for this, and OpenVPX compatible. A 3U VPX card with, at the time, the latest, in this case, a Vertex 7 technology, but with the capability of large amounts of memory, of course facilitating the ability to process the amount of data and do it in a very quick fashion, with the FMC side on board. And an FMC that actually met the requirements, the bandwidth requirements for this particular application, taking advantage of advances in miniaturization, the latest and greatest chips that could handle the A to D and the DDA requirement. And the third-party modules, of course, both the single board computer, GPU, as well as external equipment such as transceivers, et cetera. So advantages here, prove everything out. Now you have a platform for continued development. And now the next step is to migrate it to the deployment system, which was actually going to go reside on the aircraft. So the key part here is that through this process, it was possible to maintain the same level of modularity, reuse the same elements from the lab system, and put it on the actual aircraft. Partnerships were also key here, as the development of the chassis was through working through a specialist in that area. Another key innovation here was actually taking what is traditionally a monolithic backplane, breaking it in half, putting it back to back, such that you got the elongated form factor, but in a very condensed space. So that way, again, the same exact modules, the same algorithms could cleanly go straight from the lab straight onto the system as well. And not only that, in working, the transceiver itself was a custom development, but that was able to be mated to a VPX module, allowing the engineer to essentially conserve a lot of space and use one of the 3U VPX modules, or I'm sorry, 3U VPX slots as part of the system. So integrated LRUs were also designed along with advanced cooling to simplify the maintenance and ensure reliability. And one of the big, when we talk about swap, and one of the big benefits of this approach was that the existing system went from 160 pounds down to 40. So 4 systems were replaced by 1. and forcing the engineer to essentially have to add ballast because now it weighed too little and maintain the weight requirements of the aircraft. So hopefully this gave you a sense of the importance of working with standards and the fact that there are many advantages to working with a modular approach. These include cost reduction through the methods that I mentioned before, being able to deliver systems on time, and reducing risk as well as complexity. Thank you.